Electronegativity and polarity. This explains why oil and water do not mix. We mentioned that earlier. So water molecules are polar. We learned how to identify polar molecules. Let's just review that real quickly. Here's a Lewis structure for water. And when we look at it, we see that there are two lone pairs on the central atom. That means it's going to be polar. So water is polar. What happens with a polar molecule is that they can interact more strongly with each other than nonpolar molecules can, because one end is more negative and one end is more positive, and the positive end is attracted to the negative end of another molecule. And so they have a tendency to stick together more than a non-polar molecule will stick together. So just like magnets are attracted, the south pole of a magnet is attracted to the north pole of another magnet. So polar molecules have dipoles. They essentially have a north and a south pole, and they are attracted to each other like magnets are. So there are relatively strong interactions between polar molecules. The interactions that occur between a polar molecule with a nonpolar molecule is not as strong. So what happens with oil and water is similar to what would happen if you took, oh, that stylus is just dead. If you took magnetic marbles and regular glass marbles. So these solid colored marbles are magnetic, and the glass marbles are not. And if you throw them all together, what's going to happen? The magnetic ones are going to stick to each other. They're going to bunch up, right? And the glass marbles are just going to be pushed out because of the attractions between the magnetic marbles. The same thing happens when we mix oil and water. Water is a polar molecule, and so the molecules are attracted to each other like these magnetic marbles are. And so they stick to each other. The oil molecules are nonpolar. They have very, very weak interactions, and so they just get pushed out just like the glass marbles do. Does that make sense? The water molecules like each other so much that they exclude other molecules. So this is like a clique in high school, right? The Mean Girls clique or whatever. And those girls are just so tight with each other that nobody else can get in. And so that's what happens with water and oil. The oil goes to the top because it's less dense than the water. There are other nonpolar liquids that are also excluded from water that are more dense, and they'll actually sink to the bottom, and the water will make a layer on top. Any questions? Have you ever wondered why soap does what soap does? How soap works? How does soap work? Why does that help get stuff off your hands? So if you're making a pie, which, Thanksgiving's coming up, so I think about making pies, and you use Crisco, and you get Crisco on your fingers, or if you get butter on your fingers, you can't just rinse it off with water, can you? It's going to stick. You have to wipe it off with a paper towel and then get the rest of it off using soap. If you've been working on the car and you get black grease on your hands, you need some strong soap to get it off. Because the grease and the oil are nonpolar, they don't interact with the water, and so the water's all tight with itself and just rolls on past, and the grease and the oil stay on your hands. So what soap does is it sort of acts as a mediator. So here we have an illustration of a soap molecule. A soap molecule has a polar head that can interact with the water, and then it's got this long nonpolar tail that can interact with the grease. So if you think about perhaps these two different types of substances speaking different languages, I'll pick on the Japanese and the Swedes because I'm Swedish, my husband's Japanese, and it can't be, you can't be discriminating or anything if you're doing it about yourself, right? So I don't want to offend anybody. But let's pretend that the this polar end here is Swedish. The polar people are Swedish. They live up near the North Pole, so that makes sense, right? So water's polar, it only speaks Swedish. It's not going to interact with the oil molecules who only speak Japanese. Can you imagine a room full of people? Half of them speak Japanese, half speak Swedish. Are they going to mingle around? No, they're going to form little clumps and speak their own language to each other. So the soap molecule kind of acts as a translator, an intermediary, because it can speak both languages. So it can speak Japanese to the nonpolar, and it can speak Swedish to the polar. And so what it does is it actually, I'm mixing my metaphors here. It reminds me of the pioneers circling their wagons. So here you have a chunk of oil, and you're trying to get this to wash off. Well, the nonpolar part of the soap molecule can interact with this yucky little piece of oil. And so the tail of the soap molecule can get all down in that oil stuff. And then the polar ends are going to stick out. And what this forms is something called a micelle. I almost wrote Michelle. That's not right. Micelle. So the polar ends are all on the outside. The polar ends can interact with the water. And so we have this soap surrounding smallish pieces of the grease or the oil. And then the outside can translate and interact with the water, and then this can float away. And that's how soap works. Any questions? The concepts of polarity in terms of molecules are really, really important in how things interact with other things, the chemical properties of substances. There, we finally finished that chapter.